When an agent faces an infinite sequence of potential decisions, we need a mathematical guarantee that our calculations will actually arrive at a solution. To find that guarantee, we have to look at the geometry of the state value functions. This geometry exists within the value space, denoted as our script. If an environment has 10,000 possible states, this space is exactly 10,000 dimensional. Here, a single coordinate represents an entire state value function, a complete mapping of every state to its expected return. To evaluate convergence, we must establish a way to measure the distance between any two points, or value functions in this space. Standard Euclidean distance is insufficient here, as it can mask local errors by averaging differences across the entire space. The correct metric for this geometry is the infinity norm. This equation defines distance by finding the maximum disagreement between two functions. Visually, if we plot two value functions as surfaces over a state space plane, we draw vertical lines connecting them at every coordinate. We evaluate the absolute difference between these two surfaces at every single state. The system identifies the one state where the functions differ the most. That single maximum value becomes the official distance between them. This specific metric allows us to introduce operators that act on the value functions, using the discount factor to compress the maximum error across the entire system. The Bellman expectation operator takes an existing value function, applies one step of the environment's dynamics under a fixed policy, and outputs a new one. We can prove this operator brings functions together by measuring the infinity norm distance between an updated function u and an updated function v. Note that the reward term r pi cancels out. Since the policy is fixed, the immediate reward for both functions is identical. It shifts both absolute values by the same amount, which means it cannot change the distance between them. This leaves us with the discount factor and the transition matrix multiplied by the difference between our original functions. The transition matrix factors out through state probabilities. At a single state, this multiplication is an expectation. By the triangle inequality, the absolute value of a sum is less than or equal to the sum of absolute values, which we replace with the global infinity norm. In any Markov decision process, probabilities of moving to all possible next states must sum to exactly 1. Since they sum to 1, the weights vanish, leaving the original distance multiplied only by the discount factor, gamma. Because the discount factor is always between 0 and 1, the expectation operator is guaranteed to compress the distance between any two value functions. The Bellman optimality operator, B star, is different. Instead of following a fixed policy, it selects the action that yields the highest expected value. This max operator is nonlinear, which means we cannot use the same linear algebraic factoring we used for the expectation operator. If function u and function v choose different optimal actions, we must prove that the difference between their resulting peaks remains bound. We solve this with an auxiliary inequality. If we compare the absolute peaks of two functions across identical actions, the peak difference is less than or equal to the maximum matched difference. This gap remains tethered to the matched limit. Applying this to the Bellman optimality operator, we pull the absolute difference inside the max operator. This forces matched actions, meaning identical rewards cancel out. Since transition probabilities sum to 1, the distance remains firmly bound by the discount factor. This same logic extends to action value spaces. Although Q functions are larger, mapping every action in every state, the underlying transition dynamics and reward structures still follow the same probability rules, ensuring the contraction still holds. By binding the peaks of different functions to their matched components, the optimality operator maintains a strict contraction. We can now see the outcome of this geometry within the value space. You can begin the process with two completely different, arbitrarily initialized value functions. Apply the optimality operator once, and the distance between those functions is reduced by the factor of gamma. Apply it continuously, and the surfaces are drawn closer with every iteration. Since gamma is less than 1, this loop drives the distance toward 0. The surfaces converge until they occupy the exact same coordinates, reaching the unique fixed point of the Bellman equation. If this operator always brings the space together, what is the specific point it is forced to find?